What is ultra-high pressure metamorphism? This is a process by which structural and mineralogical changes in rocks are caused by ultra-high pressure. These pressures are high enough to stabilize calcite at pressures exceeding 2.5 gigapascals and occur in subduction zones at depths greater than 100 kilometers. Ultra-high pressure metamorphism occurs when buoyant continental material is subducted to depths greater than 100 kilometers and is eventually exhumed back to the surface. These rocks contain extremely unusual crustal materials such as calcite and microdiamond. The subduction of continental crust leads to subduction zone-like cold temperatures at high pressures. High and ultra-high pressure metamorphic rocks are indicative of regions where crustal materials have been subducted to mantle depths and then exhumed. The rocks and terrains provide insight of the dynamics and conditions of subduction and continental collision zones. Three main groups of crustal materials are metamorphosed under ultra-high pressure conditions. These are accretionary wedge sediments, which produce mainly blue schists, oceanic crusts producing mainly quartz eclogites, and continental crust producing quartz and calcite eclogites. Here we can see an eclogite, which is a characteristic rock of ultra-high pressure metamorphism. It is also known as the Christmas tree rock due to the characteristic red and green colouring, where mafic minerals are metamorphosed to anthracite and garnet during prograde metamorphism. The main mineral indicators of ultra-high pressure metamorphism are calcite, which is a polymorph of silica, and microdiamond, a high-pressure polymorph of carbon. The distinguishing indicator between high-pressure and ultra-high pressure metamorphism is the mineral calcite. Ultra-high pressure metamorphism occurs in the deepest part of the eclogite facies, which is the dark green area seen in this diagram. This represents the calcite stability field. Ultra-high pressure metamorphic terrains are found across the globe and are identified on the basis of calcite or metamorphic diamond occurrence. The oldest terrain discovered was from the Mesoarchean, and the youngest was from the late Miocene to the Pliocene, found in Papua New Guinea. Does buoyant crust get subducted? The leading edge of a continental plate is entrained into a subduction zone by the sole effect of body forces. The continental margin is thinner and the cohesion between the continental and sinking oceanic lithosphere is higher, therefore burial. Subduction acts like a conveyor belt. The plate starts out as oceanic crust and converts to eclogite at depth. Eclogite is denser than upper mantle and sinks, pulling the more buoyant continental crust down with it. In the case of ultra-high pressure metamorphism, what goes down must come back up. This process is known as exhumation and is less well understood than subduction. The persistence of calcite and microdiamond during decompression is a result of their inclusion within strong host minerals such as garnet and zircon, which act as pressure vessels, preventing their retrograde metamorphism. Most ultra-high pressure terrains that are presently exposed are comprised of light upper crustal material, which is the role of buoyancy. The petrographical record suggests that decompression occurred under continuous cooling conditions. Isotopic dating shows that formation ages and cooling ages of ultra-high pressure rocks span a narrow range of a few million years and a high decompression rate. Exhumation rates of between 1 and 2 centimeters per year closely match plate velocities. Therefore, the most likely exhumation path is a two-way street where they return back along the subduction channel after slab breakoff. This process is demonstrated in this laboratory model.